This is 1.4, Day 5 notes. I'm Mr. Bishop, and in these notes we're going to talk about formulas for linear functions. So in the Day 4 notes, we talked about, if you'll remember, point-slope form for a line. So all you need to make a line is a point from that line and the slope. It looks like this: y minus y1 equals m times x minus x1. And you've definitely used this before. I'm talking from Algebra 1 and even after that. So we'll continue to use it. Remember, you only replace the x1 and the y1 with the point values. Those are the ones you replace with actual numbers, and obviously m, the slope. The x and the y without the subscripts, those are the variables. Those aren't going to be replaced with numbers. We're going to keep those. So that's point-slope form. It's my favorite. The other one would be slope-intercept form. You've seen that. That's y equals mx plus b. Let's go ahead and start with example 1. So I want you to find a formula for the linear function f. You could call it f of x. A lot of times we just call it f. Given f of 4 equals 10 and f of 12 equals 16. So just given this much information, can we find a formula for the linear function f? Keep in mind, what two things do you need on a graph to write the equation of a line? You just need 2 points, right? That's what's being communicated here. So these actually just represent 2 coordinate points on the line. It's just up to us to identify which one's x, which one's y. And then we can make the slope, use the point, and so on. So we know points. We got 4 comma 10, right? 4 is the input for x. The output would be 10. 12 is the input for x here. The output's 16. So 4, 10, and 12, 16. That's what you got to be able to pick up from this. If you can do that, the rest of this stuff is easy. You've done it before. You got 2 points. What's the line? That's a mastery skill. So we got our x, our y, our x, our y. We'll start with the slope. Subtract the y's on top. So I got 16 minus 10 on top. And then just keep in the same order when I subtract the x's, I got 12 minus 4 on the bottom, which gives me 6 over 8, better known as 3 over 4. Excellent. We got the slope. We figured out 2 points. So now, to write an equation, let's use one of those points, your favorite one. I usually pick the easier ones, you could say. 410, it's got smaller numbers. So how about we pick 410? You could pick 1216 if you really want to. We'll get the same answer. It'll be equivalent. They're both points on the same line. So I'm going to pick 410. I'm going to throw it in point-slope form. Got my favorite point, got a slope. So if I use 410, it's y minus the y value equals m, the slope, 3/4, times x minus the x value. Don't forget those parentheses. And you'll notice anytime I plug values into a formula, I always, like the 10 and the 4 here, I always use parentheses on those two, just to signify that I substituted something in that step. Now, as far as being a linear equation, this is it, right? There's an equal sign, there's an x, there's a y. So that component, writing a formula or writing an equation, we've met that goal. The formula part, that's done. There it is. There's an equation, there's an equal sign, x and y, check. We don't have it in function notation yet, though, which basically just means can we replace y with f of x? And in this case, we're just going to solve for y and put it in slope-intercept form. So let's start by just distributing that 3/4 through, add 10 to both sides. 3/4 times 4, the 4's will cancel, you get 3 right there, right? Add the 10 over, and we're looking at y equals 3/4 x plus 7. Still an equation, right? Doesn't look a whole lot different than the one before. So that formula piece, that equation component, that's met. Now let's just put this in function notation. Just replace y with f of x. So put it in function notation. So we have f of x equals 3/4 x plus 7. There's our linear function f. All right, let's go ahead and look at example 2. It's a supply and demand scenario. Supply and demand. 2 components to this one. The first one being price of an item, and the second one being the number sold. So price, we're going to let that be P, and then the number sold, that's going to be Q, and then go ahead and construct this table. The top row is price P, that's in dollars. The bottom row is the number sold, that's going to be our variable Q. And so we're going to look at what happens as the price of this thing changes. So let's give a couple, 3 different prices. So the first one's 50 cents, 75 cents, $1. And maybe these represent drinks out of a vending machine or something. I'm not sure. The number sold, you could probably guess what the trend's going to be, right? If it's cheap, you sell more. You double the price, you don't sell as much. So I'm going to give you values for that too. So the number sold, 1,500 at 50 cents, 1,000 at 75 cents, and then 500 at $1. So we've got a table here. You probably know what I'm going to ask. Given this information, can you construct a linear equation? Maybe it doesn't even appear linear to you. Hopefully we can kind of see a linear trend. If I just look at the bottom here, the number sold, that's decreasing by 500 at each increment, and then the price, as that goes up, 25 cents at each increment. So it looks like they're both increasing at a constant rate of change for the consecutive terms. But when we go to write the slope, we know it's y is on top, x is on bottom. So which one of these would be on top and which one would be on bottom? Well, in terms of a company, they set the price, right? So supply and demand, they set the price at whatever they'd like to. So that will be the independent variable. And then the number sold very much depends on the price, right? If it's really expensive, and let's say $1 is really expensive for this beverage or whatever, they don't sell as many. So that would be the dependent variable, the number sold. So that's like our x, the price, it's independent, and our y would be like the number sold. So let's go ahead and get a slope. And you might be able to, again, just observe it. Looks like it goes down 500 for every 25-cent increase. Or, if that doesn't make sense to you, just grab a couple points here. Let's throw it in the slope formula. So 1,000 minus 1,500, I'll use these 2 points. And on bottom, 75 cents minus 50. So the y's are on top, the dependent variable, the number sold, that's on top. And then the independent variable, the x's, will be our price here. Those go on bottom. We should get negative 500 over 25 cents, and that's the trend I was trying to point out. You might have been able to just observe that and not even have to do the equation here. So negative 500 divided by 0.25 gives us negative 2,000. We're going to have to be careful with the units here because we will have to interpret this at some point. So the 500 came from the dependent variable, the number sold, and on bottom was the price. So we have the number sold over the dollar amount. So you can think about that as being negative 2,000 over 1, right? So if I think about for every $1 increase in the price, it looks like we're losing 2,000 items sold. So you don't sell as much when the price goes up. For every $1 increase in price, you can expect to lose 2,000 items as far as the number you're going to sell. All right, great. So we got the slope. We know how to interpret it. That's not the only component we need, obviously, if we're going to write the linear equation. We got some points, though, so why don't you pick your favorite one and throw it into point-slope form. And my favorite one in this case, the one I think is easiest, would be $1 for the price and 500 for the items sold. So 1 comma 500 will be the point I would use. So let's go ahead and throw it in point-slope form. And I'm going to use, instead of x and y's, I'm going to try to use p and q. And you can throw it in, you can use x and y's to start. I'm going to try to use p and q here. So let's see. It's usually y minus y1. So how about q minus y1 or q1, this value, equals m, the slope, times x, or in this case, the independent variable is p, minus that x point or in this case, the P point is $1. So I went ahead and threw it in point slope form and use P and Q instead of X and Y. But if it helps you to use X and Y to start out and then replace P and Q at the end, feel free. So technically, this is a linear equation right here that relates P and Q. There we go. That's done. That meets the criteria. I'm going to go ahead and solve this one for Q, though, so we can have it in slope-intercept form. And that's actually pretty easy to do. We just need to just distribute this 2,000 and then add the 500 over. So let's go ahead and do that. Distribute that 2,000 and then add the 500 over. You should get negative 2,000p plus 2,500 as your answer for Q. Another way you could have written the Q part, you could have said, and I'll add it right underneath here, you could have just said Q of P, right? Because we input P. You tell me what the price is, and I'll tell you how many you can expect to sell, right? So the independent variable, you just tell me what you're going to set the price at, and this equation, what it does is it tells you the answer for Q, the output, how many you can expect to sell. So instead of Q, you could have had Q of P, right? We could say Q, the number you sell, is a function of P, the price the company sets the item at. All right, let's go to example 3 then. We'll play a little game called Is It Linear? So is the function linear? Okay, and this is just to check. People throw all sorts of different kinds of functions at you, and can you sort through them and say which one's for sure linear and which one isn't? So what are some characteristics for sure you know of linear functions? Well, they can be written in the form y equals mx plus b. That's slope-intercept form right there. Another trait you know for sure linear functions have, they're a polynomial of degree 1. What does that mean to have degree 1? Well, that means on the variable x or the variable y, the exponent would just be 1, right? Now, we don't have a 1 written in there, but that's what's implied. It's definitely not squared or cubed or square root. So linear functions are polynomials of degree 1. What else do you know about linear functions? For sure, you know what the graph makes, right? The graph makes a line. Okay, so let's take a look at a few of these. Part A, here's a function, f of x equals 2x squared minus 1. Is it linear? And right away, I hope it jumps off the page you say no. I mean, obviously it breaks the rule of being degree 1. This is degree 2, right? The x is actually squared. So this isn't a linear function at all. In fact, this is a quadratic function. So part A, that's a big no. Part B, f of t equals 4t to the negative 1 plus 9. Again, we don't have to use x and y's, right? We can use any variables we want. In this case, we have t. So I hope this one jumps off the page at you too. T to the negative 1 is no good. That doesn't make any sort of line. This one's a big no. In fact, if you remember the rules from exponents, t to the negative 1, you could write that as 1 over t. Move that t to the denominator, plus 9. Doesn't look anything like a linear equation. All right, part C. G of x equals 9 plus 4x. Now, I know we have 2 no's in a row. Don't be fooled by this one, though. This one's absolutely linear. Just because the 4x and the 9 are not in the places you're used to, like if you use y equals mx plus b, you could easily write this as 4x plus 9 instead of 9 plus 4x. This one's absolutely linear. That's a big yes. All right, last one here, part D. A equals pi r squared. So instead of x and y, we can use a and r as our variables. And I hope you recognize this from somewhere. A would be the area, r would be radius. So this formula actually gives you the area of a circle. And the fact that the variable here, the r is squared, right away, that's not degree 1. This is a big no. In fact, this would be another example of a quadratic equation or quadratic function. All right, and then some characteristics you probably know, maybe you forgot. Let's refresh on. How do parallel lines compare to each other? They share some of the same qualities. What do you know about parallel lines? They absolutely have the same slope, which should make sense, right? Graphically, the average rate of change, they're sloping at the same rate, which is why they'll never cross. How about perpendicular lines, though? And I hope you guys are okay with my perpendicular symbol, if you remember that from geometry, or my parallel line symbol. Perpendicular lines, they don't have the same slope. In fact, they have completely different slopes. To be specific, their slopes are opposite reciprocals. Opposite reciprocals. So a common mistake, kids mix these up. They don't know what these words mean. So they're referring to two different things. Opposite refers to the sign, positive or negative. So in mathematics, anytime you hear the opposite, that's referring to sign, positive or negative. Reciprocal, that's the part that refers to that flipped fraction thing. So if I said 3/4, you would say the reciprocal is 4/3. So let's keep those straight. Opposite refers to the sign, reciprocal refers to flipping the fraction. Now, if you're a perpendicular line, your slopes are opposite reciprocals, so you have to do both. Change the sign and flip the fraction. All right, so example 4, this is the last example for these notes. I want to take a look at a couple different sets of lines here. Part A, y equals 2x plus 1, that's one line, and then y equals negative 2x, or excuse me, y minus 2x equals 4. What do you think? How are they related? And the easiest thing to do here is, this one's really, like, we can think about this one pretty clearly. Y equals 2x plus 1 because it's solved for y. Let's make one move and solve this for y. Add 2x to both sides, and it's really easy to see that at that point. Y equals 2x plus 4, another way to write this. So if we compare, slope here's 2, slope here's 2, these lines are absolutely going to be parallel. That's the relationship between those two lines. Fun one to spell. P-A-R-A-L-L-E-L. All right, part B. Y equals 3/2 x, 3 over 2x, minus 2. And y equals negative 2/3 x plus 9. So I'm thinking right away that these are perpendicular. Does it meet both criteria? Opposite, sign switched, yep, that one's positive, that one's negative, and reciprocal. Well, this one's 3 over 2, this one's 2 over 3. So if you look and compare the slopes, that's all you got to focus on here. Compare those slopes. These lines are perpendicular for sure. The slopes are opposite reciprocals of each other. And the last one here, part C. Y equals 3x plus 4. And then the next one, linear equation still, just looks a little different. Negative 12x plus 4y equals 16. Okay, and sometimes to be able to assess these really well, we need to make this look different, right? We need to put this one in slope-intercept form, just how the y equals 3x plus 4 line is written. So to do that, why don't we add that 12x over and just divide everything by 4, and that should get us there. Add the 12x on both sides, so we got 4y equals 12x plus 16. Thankfully, everything in here is divisible by 4. It's going to work out nicely. So divide that 4 out. We get y equals 3x plus 4. So something that might not have been obvious to you, like right from the get-go, this might not have been obvious. Y equals 3x plus 4, what do you know? So certainly not perpendicular, and parallel would be wrong too. Parallel lines never cross. We got the same line here. So this would be neither parallel nor perpendicular. In fact, we did a little work to discover it's just the same line written a little different way. All right, so we looked at characteristics of linear functions, talked about point-slope form, and a little about slope-intercept form too. That's all for these notes. I'll see you in class.